and welcome. Ever stop to think about the invisible architecture all around us? The pushes and pulls holding literally everything together. Well, today we're going to pull back that curtain. We're going to demystify this powerful hidden world of what we call force systems. So yeah, let's just dive right in.
So let's start with a really big question. You ever look at a massive bridge or maybe a skyscraper and just wonder, how do they know? I mean, how do engineers know for sure that thing is going to stand up and not fall down? Well, the secret, it's all about understanding and, more importantly, organizing all the forces acting on it. Okay, so where do you even begin with all that? It feels like chaos, right? Well, before you can even think about doing any math, the very first step, and honestly the most important one, is to bring some order to that chaos. You've got to classify all those forces, sort them into nice, neat little categories that you can actually work with. And this right here, this is basically the roadmap. It's the flowchart that engineers use to sort every single push and pull you can imagine. Think of it like the blueprint for figuring out, well, anything, from a simple little lamp hanging from the ceiling to a super complex machine. And that's the key takeaway, right? It all starts with classifying these forces. So, if you look at our roadmap, the very first big decision we have to make is actually pretty simple. Are we dealing with forces on a flat, 2D surface, or are we talking about forces out here in the 3D space that we all live in? And that question gives us our first two big buckets to sort things into. First, you've got coplanar forces. That just means all the forces are lying on the same flat plane. The easiest way to think about it is like a drawing on a piece of paper. Then you have non-coplanar forces. These are the ones acting in 3D space, which, let's be honest, is how most forces in the real world actually work. Okay, check this out. This visual makes the difference totally obvious, right? On the left, you see all those forces are sitting nicely on a flat 2D plane. But look at the one on the right. Those forces are pointing every which way inside a 3D space. It's a whole different ballgame. Now, just to keep things simple for now, we're going to focus on that flat 2D world to really nail down the basics.
All right, so let's zoom in a bit. Now that we're in this 2D flatland, this world of coplanar forces, we can break it down even more. Turns out there are three main types of systems here. First up is what's called the concurrent system. And yeah, the name itself kind of gives it away. Concurrent. It sounds technical, but it's really just a fancy way of saying that all the forces, if you were to draw lines through them, would all cross at one single point. A great way to picture this is a tug of war, but with ropes going in a bunch of directions. Everybody is pulling on that one central knot. All the action is happening at that one spot. And this example here, it's perfect. You see the tension in those two strings? And then you've got the weight of the lamp itself pulling straight down. Where do they all meet? Right there at point A. That is a textbook concurrent system. Okay, so we've got forces that all meet up at one point. What about the complete opposite? What about forces whose paths will never cross? Well, that brings us to our second type, the parallel system. And this one is exactly what it sounds like. In a parallel system, all the forces are running alongside each other, perfectly parallel. Think of lanes on a highway. They're all going in the same direction, but they never, ever intersect. And here's a super simple way to think about it. You've got a few people sitting on a bench. The weight of each person pushes down. The weight of the bench itself pushes down. What do you have? A bunch of forces, all caused by gravity, all pointing straight down. They're all parallel, it's clean, it's simple. Okay, so we have concurrent, where they all meet, and we have parallel, where they never meet. But what about everything else? All the situations that don't fit into those two tidy little boxes. Well, that's what our third and final category is for. It's called the general system, and it's pretty much the everything else bucket. The forces are still in that same flat plane, but they're not all meeting at one spot, and they're definitely not all parallel. It's just, a general mix of forces doing their own thing. Just take a look at this plate here. You've got forces coming in from all different directions, at all different angles. They're all on the same flat surface, sure, but they don't meet up at one single point, and they're obviously not parallel. Bam, that's a general system. All right, now let's talk about something really cool. It's a handy little shortcut, almost like a magic trick that engineers use to make their lives way easier. It's called the principle of transmissibility. Okay, I know that official definition sounds super academic and a little dense, but the idea behind it is actually really simple and it's super powerful. All it's saying is this: If you have a solid, rigid object, you can push or pull it from any point along the line of that force, and the overall effect on the object will be exactly the same.
This train example makes it so clear. Think about it. If you want to move this train car, does it really matter if you pull it from the front or if you go to the back and push it with the exact same amount of force? As long as you're pushing or pulling along that same straight line, the car is going to move in the exact same way. The end result is identical. That right there is the principle of transmissibility. So, okay. We've spent all this time sorting forces into different systems. We've learned this neat little engineering trick. But what's the point? Why does any of this actually matter?
Because this stuff isn't just theory for an exam. This is the bedrock, the absolute foundation of all structural engineering. Knowing how to spot these systems and how to analyze them, that is the number one most important step to make sure that the bridges we drive on, the buildings we work in, even the chair you're sitting on are safe, that they're stable and won't just collapse when you use them.
So here's a little challenge for you. The next time you sit down on a chair, or walk across a bridge, or even just glance up at a light hanging from the ceiling, pause for a second. Try to see that invisible architecture we've been talking about. Can you figure out what kind of force system is at play, quietly holding your world together right in that moment?